Okay, so I gave you this exercise in the previous video, and you need to calculate the p-value based on the t-statistic. You need to, that is, the t-statistic is 3, so the p-value is the probability outside plus minus 3, because you have to consider like negative shock equally as the positive shock. And then you can calculate 0.270%. And suppose that the significance level is 1%. Then can you reject the null hypothesis or not? It's the last step, right? Just call the decision. What is your decision? So let me give you the answer. 0.27% means if you rank the outcomes from the most unlikely to the least unlikely, I mean most likely, then what you observe is the very unlikely outcome, top 0.2% unlikely outcome. So if your significance level is 1%, that means you are going to reject top 1% unlikely outcomes to which your observation is included, right? So you have to reject it. Your outcome is too much unlikely, so you are going to reject it, right? So then let me casually explain what happened. So I believed the study hour for the final exam was 50 hours. So the mean was 50. But but the survey sample average could be different from 50 hours, but according to the normal distribution. So a normal distribution random error can happen. Sampling error is always normal, right? But I happen to have 56. This is possible. This was possible even if so suppose that my belief is true, then if I happen to choose a lot of hardworking students, then they drive up the sample average, so I could get a sample average of 56, which is 6 hours more than my guess. But now then what you need to think about is, so to understand it this way, to think about this chance, you have to meet a lot of hardworking students. How likely is that? That percentage can be calculated. That is 0.27%. It's like, so meeting, you have to meet like hardworking students many times, which is unlikely. It's like you just, or some accidents happened for each of your reservation. So you are not an abuser, but you needed to cancel the reservations. Similar, so you it is possible that you can see many hardworking students by chance, but that is too much unlikely. So you cannot believe it. You cannot believe it. It's right. So I would it is more reasonable to just give up the belief rather than rationalize the belief with that small probability, right? That's how we implement hypothesis testing. Okay, so now let me discuss 3 different ways to make the decision. So basically, the underlying method is the same, but in practice, 3 different methods are used to implement the same thing. So I will be more specific about those methods. So I will start from this hypothesis. I will assume that a hypothesis is about the population mean equals a certain number. Mu zero is a number. You can think it as like 30 or 50 in our example. And the three ways to present the result of a hypothesis test will be discussed. By the way, you can think it this way. Different programs have different ways to put the command, write the command of this hypothesis testing. So, and there are 3 different ways you write a code, or there are 3 different ways a statistical program gives you the results. So you have to be able to understand all 3 of them. I'm going to show you the 3 different ways. First, some program gives you p-values so that you can calculate, you can reject it or not by yourself. Or in other cases, t-statistic is calculated, and you may use the t-statistic to make your decision. And finally, in some cases, critical values are calculated. So, like, you know what these are, but critical value is a little bit different. So we will discuss how they are related. But in the end, they are actually equivalent. Just different ways of making the decision, right? Or and in some cases, one is more convenient. Other cases, another is more convenient. And in some cases, you may need to use a specific one. And in some cases, that method may not be possible. So that's why we need to learn all 3 of them. So p-value approach is exactly what I explained so far. I first calculate the sample average, and then I standardize the difference between the observed sample average and your belief. Standardize, and then use the standardized t-statistic to calculate the p-value from the standard normal distribution. And finally, the final result is the p-value, and this is reported. If the p-value is reported, your decision rule is based on the p-value versus alpha. If p-value is too small, smaller than alpha, reject. Not, right? If greater, don't reject, right? So this is how p-value approach is implemented. And as I said, the p-value is a measure of the likelihood of the observation. If your belief was true, if my belief was true, then I can calculate the likelihood of my observation. And when you calculate the p-value, we need these guys: x bar, standard deviation, and sample size. So that means when you have a different data, when you have new data, then you have to recalculate all of these. Recalculate the p-value. So that's that. But what's good about this is when I give you the p-value, decision making is pretty simple. You just compare the p-value with your own alpha. Alpha is a subjective choice. It's your choice how generous, how strict you are. So just simply compare p-value and you can make the decision. So just computer does the computation and decision is made by you. You choose alpha and make the decision. So this is a most common way to implement the hypothesis testing, and when usually p-value is often reported to give you to show the results. However, so that means alpha is not involved in p-value, so you may change alpha. So if you want change alpha, then there is no change in the p-value, so you don't need to do it again. And increase in alpha, so now you can study how alpha works. If you choose higher alpha, then means you are rejecting more, right? More likely to reject the null hypothesis. So for example, suppose that H0 is rejected at 5%. That means, and if you increase the significance level to higher than 5%, then always it will be rejected. But if it's smaller than, because it means that p-value is smaller than 5%. So if again, if the null hypothesis is rejected at 5%, that means the p-value is smaller than 5%. So no matter what significance level you choose above 5%, always it is rejected again. So higher p-value, higher significance level will reject more. Vice versa, if H0 is not rejected at 5%, then that means p-value is greater than 5%. So you don't need to think about p-value significance level smaller than 5% because will not be rejected either, or like not rejected automatically by definition, by construction. So this is like how alpha and p-value are compared. And now you can understand what happens if alpha increases or decreases. Okay, then second approach is the t-statistic approach. Now the first two steps are actually the same. You calculate the sample average and then standardize. But earlier we had the third part where you use this t-statistic and plug that into the standard normal distribution. But now I don't do it. I'm not going to do it. I will make the decision right here directly from the t-statistic. Then you may understand it this way. So remember, t-statistic is the standardized difference between the observation and your belief. So the larger the t-statistic is, the larger the difference is, then the more unlikely the less consistent your belief is with the data, right? So the bigger the difference, the more likely to reject your null hypothesis. So we can define the decision rule this way. We are going to reject the null hypothesis if the standardized difference, t-statistic, this guy, is large in this sense. The absolute value is greater than alpha. That means t is greater than plus a or smaller than minus a, right? And the other case, don't reject. Otherwise, you don't reject, right? If the difference is reasonably small, then you don't need to reject your null hypothesis. And then the question is, how do we choose this cutoff, right? How do we choose this cutoff? We try to make it consistent with, we choose that value, that cutoff, to be consistent with the p-value approach. So in the p-value approach, significance level played that role. It's exactly here, significance level was playing that role. So now this value is determined by the significance level. That means, remember, the significance level is the percentage of rejection. Like in the ranking, you reject alpha probability from the top. So then in the normal distribution picture, graph, if you reject alpha probability, you are going to reject alpha over 2 from the top and reject alpha over 2 from the bottom. You have seen this before, right? In the confidence interval chapter. We are applying the same idea, and then you will get A equals Z subscript alpha over 2, which is top alpha over 2 probability value. So in the end, the decision rule becomes this way. So I'm going to choose the cutoff at Z alpha over 2, which depends on the significance level. And if the the standardized difference is greater than the cutoff, you reject the belief. The belief is too much different from the null hypothesis. From the data, excuse me. Graphically, you can understand it this way. So if you choose significance level alpha, 5%, that means you are willing to reject 5%. That means you're rejecting 2.5 from the top and the other 2.5% from the bottom. So you have to choose A so that this area is 2.5%. Exactly, this is what we did, and if you remember the numbers, it was 1.96, right? And if you choose it this way, then p-value approach and t-statistic approach are equivalent. They are equivalent. We designed the numbers so that those two approaches are equivalent, right? Okay. And then, when do you use the t-statistic approach? This is used when just it's actually more widely used because p-value is more difficult to understand. P-value is more difficult to understand, but t-statistic has a better interpretation. It is the standardized difference, and many applied people, even if they don't understand what p-value means and how p-value is calculated, but they know that plus minus 2 is the rule of thumb threshold cutoff. So if the standardized difference is in between plus minus 2, then usually that's okay. The null hypothesis is not rejected. So t-statistic is also widely used in that case. So for example, you can put this kind of interpretation. If the t-statistic is minus 2, then the observed sample mean is 2 standard error below your belief. So because of this better interpretation, possibility of interpretation, t-statistic is widely used in practice. And also, remember, t-statistic does not depend on your significance level. So t-statistic depends only on, your sample average and your belief and your standard deviation from the data and the sample size. So these three guys are from the sample and mu0 is from the belief. So it does not depend on your choice of alpha, significance level. So again, it leaves the calculation is all the computations are handled by the computer program, and the final decision, rejection, is up to you. The computer just reports you the standardized difference is this large. It is up to you if you think this difference is significant or not, so that the null hypothesis is rejected or not. And then the t-statistic is compared with z alpha over 2, which is the counterpart of the t-statistic, and this depends only on the significance level. And the idea is same as what we did in confidence interval. If alpha increases, that means alpha increases, there is more outside. So the tail probability should increases, that means the interval must be narrower. So alpha is the tail probability, outside probability. So the higher the alpha is, the smaller z alpha over 2 is, closer to 0. So higher alpha implies more rejections. And these are the common numbers. So given the significance levels, these are the cutoff for the t-statistic. And as a rule of thumb, plus minus 2 is usually used for many applied people. Again, same as confidence interval. So it is now the the last approach is the critical value approach. Now, the approach is slightly quite different from the earlier two approaches. We are going to put the decision rule this way. We are going to reject the null hypothesis if the observation is too much different from your hypothesis, right? Very natural. Then we have to define how different is too different, like, and how close is close enough. And we are going to define that as these critical values. So we will allow plus minus m. We are going to allow a certain margin around your belief. So if my belief is 30, but then I will allow plus minus, say, 3 hours around my belief. If your data is within the margin, then your belief is good. But otherwise, if the data is outside of the margin, then your belief is rejected. Something like that, very natural approach. So we are going to call these two endpoints mu 0 minus m or mu 0 plus m as the critical values. Upper critical value, lower critical value, right? Upper critical value, lower critical value. And the interval area between these two critical values is called the acceptance region, because the null hypothesis, it will be accepted in that area. But outside of them is the rejection region, because the null hypothesis is rejected. So you have like if your belief is 30, then you allow certain margin. So you have some lower critical value, upper critical value, acceptance region, and rejection happens outside of that region. So that's how it works. And what's interesting here is, so we have to make the critical value approach consistent, equivalent to the earlier approaches. So then let's borrow the t-statistic decision rule. T-statistics decision rule can be written in this way. In the middle is the t-statistic. So t-statistic, the null hypothesis was not rejected if the t-statistic is in between plus minus z alpha over 2. That means now what we want is we'd like to rearrange the inequality so that we have only x bar in the middle. So x bar is here, and here upper critical value is mu 0 plus this, and mu 0 minus this. These are critical values, right? So it is simple to show this. And then we get the formulas for the critical values. And you may think it's you have seen this before. Yes, in the previous chapter we calculated confidence interval, and then the formula was pretty much the same. Like, not exactly the same, but this part is the same. Idea is the same. Okay, then the rejection rule is clear. This is the critical value, and you are going to reject if your observation is outside the critical value. Okay, and like now let's compare the confidence interval and the critical values. The major difference here is in the confidence interval, what we are doing here is we are based on the data, and we would like to guess, we'd like to make an interval for the unknown parameter, right? Right? So we hope this interval to contain the true parameter, right? On the other hand, the critical values are calculated based on not based on the data, but based on your belief. So it is around the null hypothesis, mu 0. Mu 0 is from your null hypothesis. So, and H0, it will be compared with your observation. So the critical values may contain your observation sample average or not. So it's kind of like parallel, and it's an estimation, and it's a rejection rule. So the purpose are quite different. And finally, the name confidence level is 1 minus alpha, and significance level is alpha. This is really annoying. Even I'm confused. So please understand, even if I say say 95% significance level, then I meant 5% significance level. Or often I may say 1% confidence level. That means I wanted to say 99% confidence level. So like they are basically, flip side of a coin, but terms are pretty not unified, not consistent, not organized. I hate it, but I cannot change it. Okay, it took too much, so let me stop it here, and we are going to do some exercise in the following video. Thank you for watching. See you later.